What? How would you?
All right. So I was kind of saying it up here, but I think it'd be good to talk about it for the whole class. So we've got sections 5.2 and 5.3, and then we're going to take another quiz over sections 5.2 and 5.3. That quiz will not be until after spring break. Okay? I realize we'll have to review when we get back over those two sections. Because honestly, I feel like I could take a couple days with section 5.2 just teaching the material. And then the homework set is a little bit lengthier. So I'm planning on doing section 5.2 today, tomorrow, and maybe a little bit into Monday. And then the rest of the period on Monday and Tuesday be a work day. Okay? And then section 5.3, Wednesday, Thursday, Friday. And then that's spring break after that. Okay, so when we'll come back, we'll review a little bit, and then we'll take a quiz over sections 5.2 and 5.3. Remember that we then will do section 5.4 and then have a test. Okay, our test is sections 4.9 to 5.4. So we have one more quiz and then a test, and then we'll do 5.5 quiz 6.1, and then that's it.
5.5 and 6.1.
Yeah, they pair up together.
And then is that?
And that's it.
Yeah.
Yeah. There's a test over that, but that's all in the material.
Quiz on 5.5, quiz on 5.6.1.
I think so. I think that's what I'm going to do.
Or quiz for just a test on.
I know I want to do quiz on at least one of those two sections to give you one more quiz in there, and then a test over those two sections. Yeah. But that's it. Can you believe that? 5.2, 3, 4, 5, 6.1. Only 5 more homework assignments. Crazy, right? What did you say?
Nothing. I just wrote through that.
Did you turn in all your homework?
Yeah, I did. I have a question.
Yeah.
So after we do 6.1 and we take the test, is it just exam review and then
we'll
the exams over the whole year?
Okay, I was looking at that, and it says, I have to get a little bit more clarification. I thought the exam was going to be over the whole year, but I read something in one of the syllabi that made it seem like it was only a second semester exam. So I'm going to see, I'm going to put in a couple emails and see.
Make sure you clarify that you want to.
Derivative.
Yeah, I mean, we learned a lot of derivatives the first half.
And then we destroyed all that.
And then we destroyed everything that we learned and said, hey, forget all that, now let's just learn all the rules. Okay, so jumping back into section 5.2, what is section 5.2 about? Well, it's combining our ideas of differentiation and integration and antiderivative. Right? It's combining all of that stuff because, you know, differentiation and antiderivative, they're inverse operations, right? To differentiate is the inverse of to find the antiderivative. So we hadn't really learned how those two things related, how to find the antiderivative, or what the antiderivative is, and then this whole area thing that we had learned. Okay. Basically, what we're going to find here is, you know, in terms of the area underneath a curve, I was giving you a beginning point and ending point, right? I was saying, okay, I am going to define the beginning point, I'm going to define the ending point, and we're going to find different ways of finding that area. We chose left side, we chose right side, sometimes we chose middle approximation, rectangular approximation methods. But we're going to say, okay, what if we make that arbitrary? You know, what if we don't try to make it just left side? What if we don't try to make it just right side? What if we say we can make it any interval in between there? What if those intervals are uneven? You know, what if we make that arbitrary? How can we produce an operation that will give us that area no matter how we subdivide that area of underneath the curve? Okay. Basically, how they tie in is if I define a beginning point and an ending point, like I was saying, and that's what a definite integral is. I'm defining a beginning point and ending point. And I say, okay, if I know my start and end, I can figure out the area in between by taking the antiderivative of that function and we're running the beginning point and the ending point through that function. And the difference between those values is actually the area underneath that curve, which is pretty cool. In my opinion, I think that's pretty cool. So it's connecting two things that seem very disconnected. like finding area relates to finding an antiderivative, that's pretty interesting to me. That's pretty series recording. Stop it.
You started the video, right?
I did. So yeah, all of this is recorded. So that's really what we're going to be doing in sections 5.2 and 5.3, connecting antiderivatives with area. Okay, finding the definite integral. And again, when I talk about the definite integral is when I say there is a definite beginning point and ending point, right? So find the area underneath the curve from 1 to 3, like we had done. Find the area underneath the curve from 0 to 2, from 0 to 10, from -1 to 1, right? Finding a definite area underneath the curve. Now, again, we saw in section 5.1 that a limit of the form limit is n approaches infinity of the sum of going from 1 to n of f of xi, where we make that xi. Now, when I put an asterisk that as a superscript on that xi, that's saying that's kind of like arbitrary where we pick, not left side, not right side, but middle, but anywhere within that function, as long as it's somewhere in between those, that delta x, okay? That asterisk just means kind of an arbitrary value. So the limit going to infinity of the sum of the plugging in those x values into the function times the delta x. Now remember what we're doing there, those are just little strips of rectangles. This is the base of the rectangle, this is the height of the rectangle. That's the x value, well, kind of like the difference in the x value, that's the y value at that x value point. And that really is the limit of strip 1 plus strip 2 plus strip 3 plus strip 4 and so on and so forth until we get to strip n, right? That is just finding the areas underneath the curve. That's what we learned in section 5.1. We also saw that it arises when we try to find the distance traveled by a particular object. It turns out that this same type of limit occurs in a wide variety of situations, even when f is not necessarily a positive function, and we'll take a look at that. Even when f goes into the negatives, we can still calculate the area using this limit. Okay? In chapters 6 and 8, which you don't get to, we do section 6.1, but if you get into calc 2, in chapter 6 and 8, we will see that the limits of the form also arise in finding lengths of curve, volumes of solids. Actually, Mr. Westphal, I don't think we get into it. Maybe that's later on in chapter 5. Mr. Westphal, do you guys get into volumes? Because the AP class does get into volumes. Basically, three-dimensional area, right, which is volume. Taking the area, the volume, as you rotate a function around an axis. So centers of mass, force due to water pressure, work, as well as other quantities. We therefore give this type of limit a special name and a special type of notation. Guys, honestly, section 5.2 is just really, like looking at the homework, it's just understanding the notation, understanding the integral notation, okay? So this is our definition of a definite integral. As long as f is a function defined between a and b, so given some parameters a, b, starting point, ending point, a to b, we divide a to b into n amount of subintervals, n amount of strips that we're taking to find the area. As long as they are equal with delta x, same thing, b minus a over n, that's not changed. We let x sub 0 equal a, x sub 1, 2, 3, and so on. So our first term is going to be a, our last term is going to be b, and they're going to be the endpoints of those subintervals, and we let the asterisk s be any sample points in between those subintervals, basically not saying left side, not saying right side, just anywhere in the middle there, as long as it's within that interval. I'm taking that strip at that x value, okay, finding the y value at that particular x value. Okay, so it's arbitrary. I'm not saying left or right. I'm not saying whether it's an over. I'm not saying whether it's an under. I'm saying it's the best, basically. Okay, so xi lies in the subinterval. Then the definite integral from of f from a to b is this notation here. Okay, it's kind of like an elongated s. Yeah, it's an elongated s. That's the integral symbol, or the integration symbol. Notice that the bottom says A, the top says B. It's always the what you're going from is on the bottom, what you're going to is on the top. Okay. And then we've got f of x dx. F of x dx. That, for right now, is just a notation. And I'll talk about that again here on the next slide. But this is, this is just a notation, fx dx. Fx is the function, right? That's the function f. Whatever you're using, like we talked about x squared, we talked about 1 over x, we talked about the square root of x. F of x dx. And now that fx dx is, we don't really comprehend what that fx dx actually means, having that dx next to it actually means in our purposes right now. But basically, it's just kind of like referencing things within the sum. Because this is truly equal to the limit as n goes to infinity of the sum of I to n fxi delta x. Right? That's the area that we were just talking about, right? That's what we learned in section 5.1. So what we're doing here is we're making a notation, a special type of notation that ties in what we saw in section 5.1. It's an elongated s with the lower endpoint on the bottom, the upper endpoint on the top of the function dx. Okay, so again, we're referencing the fact that we've got to plug values into the function. Do you see that here? Right, I'm no longer calling it xi. I'm just saying, okay, it's into the function. We know that we're going to have to take sample points into that function. Dx, dx was around when we were talking about derivatives, right? It's almost like the differential on x. Okay, differential also means kind of difference on x, delta x. Okay, going from a to b, the only thing that was not in there in the limit was basically saying, okay, what are we starting from? What are we going to? Right? How do we know where our a and our b values were? I would have to give you a separate, I'd say, okay, the limit as the sum goes to infinity, blah, 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 from a to b. I would have to use a separate notation to say, or a separate phrase to say, okay, I only want the values between 3 and 5. Find the sum in between 3 and 5, right? That was never referenced within this limit. We would have to give you an extra statement to say, I only want values between a to b. Well, now I can use the notation, the integral notation, to say, okay, bottom number is a, top number is b. So basically, this is saying that notation is the area underneath the curve from a to b. That notation is going to equal the area underneath the curve from a to b. Okay. We can say that it is integrable. Oh, geez, I screw up that word all the time. Integrable, however you want to pronounce that. Integrable, I don't know. But it's just like you call something differentiable, you could call it integrable. Integrable? I think that's how we would pronounce that. Integrable on a to b. Okay. So a couple notes on the actual notation. That symbol was introduced by Leibniz. That's kind of a Leibniz notation. Remember, Leibniz was the guy that said you could call something f prime of x is the same thing as saying dy dx, right? That's Leibniz notation. Same guy. Okay, he's the guy that first started using this notation, and it's truly just an elongated s. That's all he wanted to use there, to reference the word sum. Okay, it's just an elongated s chosen because an integral is basically just a limit of a sum. In the notation a to b, fx dx, fx is called the integrand. A and b are called the limits of integration, where a is the lower limit and b is the upper limit. Okay, just taking from a to b, the lower limit of integration, the upper limit of integration. Whenever the function is called the integrand, just like what you put underneath a radical symbol is called a radicand, right? Just as the integrand. For now, the symbol dx really has no meaning by itself. This is just kind of. You got a question?
Did you get another answer?
No. You want to put that on the answer one?
Huh?
Yeah, I read it on as well. Thank you. Appreciate it. Again, right now, the dx symbol really just indicates it's the independent variable on x. The procedure of calculating an integral is called integration. Okay, that's the wording that we're going to use. The procedure of calculating the integral is called performing integration. The definite integral from a to b f of x dx is a number. Okay, that's one thing that's really important here. I'm asking for a number when I give you that notation. That number is the area. Okay, when I say what is this? What is the integral from a to b fx dx? I want the output to be a number. It's the area. It's the area underneath that curve. It's not another function. It's not, doesn't have x's in it. It's an area underneath that curve. Okay. And again, this does not depend on x, so you could use any values that you want. Like we're going to be talking about integration of time and stuff. All sorts of different symbols that we could use. The f of t dt. Just know that whatever you use inside of f of x, that's the same as you got to use on the outside with the d, right? You can't say fx dt. That wouldn't make sense. You can't say fr dt. You can't say fr dx. It's got to be fx dx, f dt, fr dr. Okay, you got to use the same variable. Just notate, just using the notation for the independent variable when you're plugging into the function. Okay.
Okay.
Thanks for the response. This sum that we've got here, and this notation should look very familiar. That sum has a special name to it. It's called the Riemann Sum. The Riemann Sum. It's named after a German mathematician, Bernhard Riemann. I think some people call it Riemann, some people call it Riemann. Basically, it's the sum, the Riemann Sum. Notice he only lived for 40 years. Yeah. He died just before the Civil War time in Germany. Not Civil War in Germany, Civil War U.S.
Bernard usually spelled like that?
In German, yeah.
Okay.
There's a guy, there's a pretty famous golfer. His name is Bernard Longer.
Isn't it usually without the H stuff?
Yeah, like an Americanized version is usually without the H.
All the Bernards I know,
Bernard. So the sum, that sum has a special name to it. I'm going to be asking you to calculate the Riemann sum. Basically, I'm asking you to do the same thing that we did last section. Just find the sum, right? You were calculating Riemann sums, but you didn't really know you were doing it, okay? You know how you calculated the sum of all of those strips? You were calculating the Riemann sum. You really were. You just didn't know it yet. So the Riemann sum basically, as an illustration here, is just basically all of the x values added together, right? All of those, or sorry, not all of the x values, all of those areas added together. We know that if f happens to be positive, then the Riemann sum can be interpreted as a sum of various approximating rectangles. But it also could be both positive and negative. It could be just negative. Like, for example, here, take a look at these diagrams, okay? If the function dips below the x-axis, well, then you would just calculate that as the negative area. I know it kind of like makes our, makes you cringe a little bit to talk about negative area because we've learned all along that area can't be negative, just like distance can't be negative, but we calculate it as a negative area, okay? Calculate it as the sum of the areas. So if I'm looking at a function like this, maybe like this is a sine curve or something like that, and I wanted to find the integral between a to b, well, then I would have to use anything above the x-axis as like a positive area, and anything below the x-axis as a negative area. And then the sum of all of those things together would be the total integral along those a to b.
So you do the positive ones and you subtract the low ones?
Basically, yeah. You could think about it as taking the positives and subtracting away the negatives, or you could think about it as treating that like a negative area and then finding the sum of all of them. Yeah. But again, the point is here is that it could dip below the x-axis, could stay above the x-axis, whatever. Now when we talk about integration, it's just basically finding the total net area underneath the curve. And when I say underneath the curve, what I mean to the x-axis. Right, the area to the x-axis. So like here, I'm going to find these areas of the rectangles from the x-axis up to the curve, and then here I'm going to find these areas of these rectangles from the function up to the x-axis, okay? It's, when I say the area underneath the curve, I'm saying the area from the curve to the x-axis, okay? All right. So, a couple more notes here. Although we've defined the integral from a to b of fx dx by dividing a and b into subintervals of equal width, there are situations where we do not use equal subintervals. Okay, there are times when you're going to use not equal subintervals. Like, you know, think about that that question you had where the person's running and we're taking snapshots of every 5 or half second, right? What if I didn't know that it was every half second? What if I used like a half second here or a whole second there or 3/4 of a second or, you know, 8/10 of a second? Okay, there are going to be times when it's going to be advantageous to work with subintervals that may be unequal, or maybe it might not be possible to take equal subintervals. That's still okay using integration. Okay, just basically still dividing it up into subintervals from a to b. We're still finding the area underneath the curve, right? So even though I may not be taking equal subintervals, I'm still finding the area underneath the curve. Okay, would it be still a good approximation? Well, we kind of have to take that for what it's worth there. Okay, just depending upon the problem that we have. Oh, that's it. There we go. We defined the definite integral for an integrable function, but not all functions have not all functions are integrable. Not all functions you can find the integral of. Yeah. Just like not all functions you can find the antiderivative of. You know, I've only been giving you functions that you can find the antiderivative of. Same thing. There are functions where you cannot find, cannot use the integral. Okay. If f is continuous on a to b, or if f only has a finite number of jump discontinuities, then f is integrable along a to b. That is, the definite integral exists, right? You can actually find the definite integral. So when would it not be integrable? I'm using up a lot, I feel like I should pronounce it correctly. Integrable. When would it not be integrable? Well, when you have an infinite sum, like when, you know, maybe it goes up to infinity and you're trying to find the area underneath that curve. That would be possible. The area would be infinite. Now, I talk about having a finite number of jump discontinuities. What is a jump discontinuity? Somebody remind me, what is a jump discontinuity?
That where it's at one point and then it moves, like the x is the same.
Yeah. So if I've got like a function like this and it's like going along and then it's like, hey, I'm going to jump down here, you know? And I said, I want to find the area from A to B. Is that still possible to find the area? Yes, that's still possible to find the area. I would basically find the area here and then add it to the area there, right? It's not like the area is going to sneak out and go that way, right? It's not going to escape there. The area is still defined. You know, I've got a finite endpoint there. You know, it would not be defined if I had said this. If I want the area, you know, and it went like this and then picked up way down there or something weird like that. Well, let me stay above the x-axis. Like here, you know, it's not defined. If this was my A and this was my B, it's not defined between certain points of A to B. It's not continuous, right? So therefore, I would not be able to find the integral from A to B. Okay, the definite integral does not exist. So this is kind of like summing everything up, right? I would write down this box that I have on the bottom of my screen here. If you haven't written down anything else, this is kind of like the summary of everything that we've been talking about thus far today. Okay, if f is integrable on a to b, then, and this is how we kind of like change forms from integration notation to summation notation. Where delta x goes from b to a over n, and each xi is a plus I delta x. See, what's convenient about the integration notation is that it has all of that information I needed within the sum, all encapsulated in one little notation. Like, I hope you guys realize that all of this stuff down here goes with the summation notation, right? Like, there's no delta x in the integration notation. There's no xi in the integration notation. We need all of that information to be able to calculate the area underneath the curve. I had to tell you all of that, or you had to be able to figure out all of that. Like on your quiz, when I asked you to find the area underneath the curve, you had to figure out what delta x was. You had to figure out what xi was. You had to figure out all of those different pieces in there. Okay? But if I have like all of that is kind of just, conveniently nice little packed away in this little notation there. Okay? How do I know where the beginning and end points are? Well, it's right there, A, B. Okay. Do I need to know n? No, because n was going to infinity, right? N was in an infinite value. Right? And I'm just saying I want those strips going from A to B, where the differential on x is my x value and the y value is my function where you plug in x. So let's practice using the notation. Okay, let's just express this sum as an integer. Sorry, did I not give you long enough on that? Did you need that, Caleb?
No.
Okay. Express that limit as an integral. Express this limit as an integral. So, what are we going from and what are we going to? 0 to pi, right? I'm going from 0 to pi. So I know I can use my integral from 0 to pi. You just put the lower boundary on the bottom and the upper boundary on the top, whatever you're going from on the bottom, whatever you're going to on the top. And then you write your function using just x values, not xi. Okay, well, my function is x to the third plus x sine x. And now your differential on x, your delta x, becomes dx. Now, be careful here. This might look like it's just x sine x dx. So I might just put that in parentheses so we can write it like that. So what's that telling you to do? Like if I wanted to go and calculate this out, I would be figuring out what the area underneath the curve was of that function, x to the third plus x sine x, between 0 and pi, and only looking at it between 0 and pi. That's what I would be doing. I can figure this out. Remember that is just equal to a number, right? That's just equal to some number, some concrete number that represents the area underneath that curve. We'll figure out, basically the rest of chapter 5 is figuring out how do we find that number. There's different ways to find that number. And it has a lot to do with antiderivatives. Again, I think this is kind of circling back to what we had before. Later, when we apply the definite integral into physical situations, it would be important to recognize the limited sum as integrals. Let's do example 1. Yeah, same thing here.
Wait, are we done with example 1?
Yeah, that was it.
Oh.
Just express it as an integral. That's it. Yeah. No. I was just trying to remind you reminding you that this equals a number. This doesn't equal another function. This doesn't equal, because like when we were doing like derivative notation, it equaled another function, right? It equaled more x values. This is always going to equal a number. This integration will always equal a number. We're usually going to use an antiderivative within the integration process, but it's going to equal a number. Yeah. Now, there are some things that you will need to know to perform integration. There are going to be some formulas and things that you're going to need to know to perform integration. These, I am going to use a couple of these when we use limits to perform integration. I am going to rely on antiderivatives and just concrete areas to perform integration. You'll see what I mean here when we start getting into more problems and getting into the homework. But I'm going to show you an example where you have to use limits to perform integration. Okay? But what's more important on this slide are the properties down below. Okay, what's more important on this slide is the properties down below. Know that if I want to find the sum of a constant, right, the sum of a constant from I to n, it's just really n times that constant. Okay? If you want to find the sum of a constant, so the sum going from 1 to 5 of 3 is just 3 times 5. It's just your n value, the number on top of the sum, times your constant. Okay, these are just algebraic rules for sigma notation, basically. That's what we're looking at down below here. If you have if you have a constant and you've got something inside the function, right? Inside the summation. If you've got like a function going on inside the summation, you can take that constant and you can actually bring it out front, right? We did that before when we said, okay, we could take our delta x and bring it out front if we wanted to, because it's really just the distributive property in there, right? A constant going into the sum, you can bring that constant out because it's its GCF. You can also break up a sum, like if you have a sum within a sum, you can break that up as the summation of A plus the summation of B. Right? If you got two different things, so say you're taking like the sum x to the third plus x squared. You can find the summation of x to the third plus the summation of x squared. You can break it up like that, and you can do the same thing with differences. You can find the sum of the difference. Just make sure it's the difference of the sums, right? Sum of the differences is equal to the difference of the sums. The sum of the sums is equal to the sum of the sums. That's a weird thing to say. Yeah.
Are we done? Yeah.
You done? That's 13 minutes class left. Come on now. All right, let's take a look here. Now, this problem is going to take me a while. This is probably going to stretch over into tomorrow, and that's okay. Maybe today we're just going to calculate the Riemann sum. That might be all we do today. Because I actually want to show you two different ways to do part B. I'm going to show you the long route. I'm going to show you the easy route. I'll do the long route first. All right, but let's show part A here. Evaluate the Riemann sum. Now, what is the Riemann sum again? The Riemann sum is the sum going from, I abbreviated RS. The Riemann sum, just the general formula, the sum going from I as 1 to n, so the number of strips going from 1 to infinity of f of xi delta x. We've done this. You calculated Riemann sum. You calculated it on your quiz yesterday. You should realize it. Okay? So we're going to calculate Riemann sums being the right endpoints. And I'm not even going to graph this thing. I'm going to do this all algebraic. See, we heavily relied on the graph in section 5.1. We're going to rely more on the algebra rather than the graph here when I calculate the Riemann sum. Now, what does this mean? Well, I've got to figure out what my delta x is. Well, my delta x, again, is b minus a over n. So in this case, it's 3 minus 0 over 6. Right? Because n is 6. I'm using 6 strips of this thing. So my delta x, my differential on x, is going to be 1/2. Now, if I'm using right endpoints, well, then my x1, well, let me talk about my xi, I guess, first. My xi is going to be my starting value, which, thankfully enough, here is 0, plus delta xi. The differences times I. So for x1 is going to be what? What's x1 going to be? Just 1/2. Right, just 1/2. x2, 2/2. Right? Or 1. x3, well, let's write them all out. x1 is 1/2, x2 is 1, x3, 1.5, x4, 2, x5, 2.5, x6, 3. Because I'm using right endpoints, I'm going to eventually get to a rectangle that has the far right side of this function as its x value, correct? If I were choosing left endpoints, I would not have that value. But you know what I would have? x1 would be 0 rather than 1/2, right? Because I would be taking the first value rather than the second value. Now, let's find the Riemann sum. Now, okay, so that's equal to, I'm just going to rewrite the notation from I1 to n of f xi delta x. Okay, so f xi is 1/2 I delta x, 1/2.
Can we change the n to 6 or no?
Yeah, I guess we can do that. Yeah.
Does it not matter?
No, it doesn't. I mean, we're calculating 6 trips, so I guess you're right. Thank you, D-Lab.
You're welcome.
We're down to this teacher's kid.
Yeah.
All right, so what are we going to do here? This is going to be delta x times the sum. See, you notice how I have this constant, 1/2? I can bring that out front because it's a constant. We know that based on this property as well, right? I can bring that constant out in front of the 1/2, or in front of the sum. And now we're going to calculate the sum by taking, okay, I want the y value at 0.5, at 1/2. I want the y value at 1. I want the y value at 1.5. I'm going to run into this list that I made over here. Scoots. Yeah, really sorry about that. You guys can't do that on your papers. Plus f of 2 plus f of 2.5 plus f of 3. Now, eventually, I'm going to want you to get to the point that you're just plugging those values in. You don't need to write the step where we have f of that thing. I want you to get to the point where you could just plug it in. So like, for example, here, this is going to be 1/2, and now I've got to calculate the Riemann sum, so I'm going to plug 0.5 into there. Let's figure out what that is. So I'd be taking 0.5 to the third minus 6 times 0.5. And I get negative 2.875. Negative 2.875. Forgive me for not showing all of the calculations. I've got them written down on my paper here, so I'm just going to write. Minus, is it really just 5? Yeah, 5 minus 5.625 minus 4 plus 0.625 plus 9. Those are all of those values plugged in. And that comes out to be, when I run that 1/2 times that whole sum, notice how some are subtraction because they're negative, right? Some are underneath. So that means I've got a negative 3.9375. That's the Riemann sum. That's the area underneath that curve. Okay, that's the area underneath that curve. We'll stop there. We won't get into part B yet. Okay, so if I ever ask you for the Riemann sum, you're basically doing the exact same thing you did last section, but now you're relying less on the picture and more on the algebraic work of it. pick up there
Who's your
tomorrow.
favorite math guy?
Favorite math guy?
That you
Ooh,
learned about.
it's gotta be Euler. He's